Welcome, curious minds, to techdaily.ai and another deep dive into the foundational world of technology.
Great to be here.
Today, we're peeling back the layers on something absolutely critical for pretty much every modern business.
Oh.
How we build, connect, and crucially secure networks in the cloud.
Yeah, it's a huge topic.
It sounds super technical, I know, but I promise you, there are so many aha moments and surprising facts waiting for us. We'll be navigating the complexities of multi-VPC AWS networks, hybrid cloud setups, and even the intricate art of internet peering.
Lots to cover.
Our mission, as always, is to give you a shortcut to being truly well-informed without getting totally overwhelmed by, the sheer volume of information out there. And this deep dive is proudly brought to you by Stonefly. They are your trusted solution provider and advisor in everything from enterprise storage and backup disaster recovery to hyper-converged VMware, Hyper-V, and Proxmox clusters.
They cover a lot of ground.
They really do. Need AI servers, a turnkey security appliance like SA365, or maybe some expert guidance on public and private cloud solutions. Stonefly has you covered. Check them out at stonefly.com for more information. Okay, let's unpack this. We've got a lot of ground to cover today. We're looking at the best practices, the cutting-edge solutions for creating network architectures that are scalable, secure, and highly available, especially as organizations, grow their cloud footprint. It's such a common story. An organization starts small in the cloud, maybe just a single account, everything seems fine, and then boom, growth hits.
Yeah, right.
Suddenly, that initial simplicity turns into this, tangled mess. What's actually happening there, and what's the recommended way to untangle that, especially as you scale your AWS environment?
That tangled mess is exactly right. The initial simplicity often hides, future requirements. Imagine a small startup. Maybe one team, one app, just a handful of resources. A single AWS account might feel totally sufficient then.
Sure, makes sense.
But fast forward a year or two, and that startup, well, it's grown into an enterprise. Multiple business units, dozens of development teams, hundreds of applications. Suddenly, that single account, it becomes a real bottleneck.
Yeah, I can see that.
The core problem here is a lack of segmentation, and the solution, the enterprise best practice, is really a multi-account strategy. It's about creating distinct, isolated compartments.
Okay, compartments, like separate boxes for different things.
Exactly. These compartments serve several vital purposes. They allow for really fine-grained control over permissions, so you can define who can access what resources with much greater precision. They make managing costs far more granular, so you can easily track spending per team or project.
Cost tracking. Always important.
Always. And they simplify environmental management, preventing accidental changes in, say, a dev environment from impacting production. This natural evolution and the need for better control and clarity as your cloud presence blossoms, it invariably leads to this multi-account strategy. That's the recommended best practice for enterprise-level cloud adoption. It's about maintaining order amidst that growth.
So how do you set up this multi-account infrastructure in a structured way? Because just creating a bunch of accounts willy-nilly sounds like it would quickly turn into its own kind of chaos, right?
You're absolutely right. Simply creating accounts ad hoc, yeah, that leads to a different kind of chaos. The solution often starts with a foundational service like AWS Control Tower.
Control Tower, okay.
When you set up a multi-account environment through Control Tower, it doesn't just give you a blank slate. It automatically provisions a well-architected foundational structure.
So it builds some stuff for you.
Precisely. For instance, it creates specific organizational units, or OUs, right out of the box to logically segment these accounts. You'll typically find a security OU, which is a really critical piece of this puzzle.
Security OU, got it.
Within this OU, Control Tower houses crucial accounts like the log archive account and the audit account. These are vital for compliance, centralizing security logs, monitoring all activities across your entire organization.
Centralized logging, nice.
Then there's often a sandbox OU. This serves as a safe playground for developers and builders to experiment with AWS services, all while staying within your organization's predefined acceptable use policies and, without risking your production environments.
So a safe space to play.
Exactly. The true aha moment with Control Tower is that it bakes these enterprise best practices into your AWS foundation automatically. It prevents future chaos before it even starts, rather than just giving you tools later. It's a pre-built, kind of opinionated structure that gives you a solid framework to build upon from day one.
Okay, that makes sense. But when you're dealing with all these accounts and Virtual private clouds or VPCs, IP address planning sounds like it would quickly become a massive headache. How do you manage that at scale? How do you prevent accidental overlaps and make sure everything can talk to what it needs to?
Oh, IP address planning is absolutely imperative. You can't build a scalable, secure, multi-account, multi-VPC network without it. Imagine trying to build a city without a street grid. That's kind of what a large cloud environment without a solid IP plan looks like.
Right, chaos.
Total chaos. Without a well-thought-out scheme, you'll inevitably run into issues like overlapping IP CIDRs, which can be an absolute routing nightmare, leads to connectivity failures, troubleshooting headaches that are incredibly difficult to sort out.
In there, not fun.
Not fun at all. A good plan considers not just your current on-premises and cloud workloads, but it proactively accounts for future expansion. Think new AWS regions, maybe additional business units joining, or even unforeseen events like mergers and acquisitions that bring entirely new networks into your fold.
Planning for the unknown.
Exactly. The goal is a hierarchical and summarized IP addressing scheme. This includes designating distinct IP CIDRs for on-prem and cloud networks right from the start, proactively preventing overlaps by design, and sizing your CIDRs appropriately to allow for significant growth without needing constant re-architecting.
And IPv6.
Yes, definitely. It also means enabling workloads for IPv6 or dual-stack compatibility. That helps reduce conflicts in the long run and addresses the ongoing depletion of the IPv4 address space, making sure your network is future-proofed.
So given that complexity, what specific tools help with this intricate IP management process? Because that sounds like a job for automation, not spreadsheets.
Automation is absolutely key here. You can use Amazon VPC IP Address Manager, or IPM, to significantly simplify this whole process. Think of IPM as like your central nervous system for IP addresses.
Okay, IPM.
It helps you organize your entire IP address space, allocate CIDRs to VPCs based on your predefined business rules, monitor IP address usage, and even share IP address space seamlessly across multiple AWS regions and accounts within your organization.
So it keeps track of everything.
Exactly. And this service actively works to prevent overlapping CIDRs. It can even automate the allocation of CIDRs to VPCs, ensuring consistency and adherence to your plan. It effectively moves IP planning from that manual, error-prone, spreadsheet-driven task to a much more automated and centrally managed one, which is incredibly valuable, saves time, prevents misconfigurations at scale.
And speaking of best practices, how does all this foundational work, the multi-account strategy, the IP planning, how does it tie into the AWS well-architected framework? Is that just a set of guidelines, or is it something more actionable for network design?
Oh, it's definitely actionable. That framework is truly your guiding star for designing and operating robust cloud systems, especially as you scale. It's not just some theoretical document. It provides real, actionable best practices across 6 fundamental pillars: operational excellence, security, reliability, performance efficiency, cost optimization, and sustainability.
The 6 pillars, right?
Right. So when you're making decisions about network design, for instance, the framework prompts you to consider how your choices, IP addressing, account structure, connectivity patterns, how they'll impact not just security, but also reliability. How resilient will your network be if something fails? And cost, are you over-provisioning? Are you selecting services that might lead to unexpected expenses down the road?
So it makes you think about the trade-offs.
Exactly, the trade-offs.
Yeah.
There's even a free, well-architected tool available right in the AWS Management Console. It lets you review your workloads against these best practices by answering a series of targeted questions. It's all about understanding those inherent trade-offs in your architectural decisions and making sure you're building a cloud environment that meets your specific business needs efficiently and securely.
Okay, so once you have your foundational accounts of VPCs set up nicely, the next big challenge is actually connecting them. Because, an isolated VPC, while secure, isn't very useful in an interconnected world. What are the common patterns for VPC to VPC connectivity?
You're absolutely right. Connectivity is key. When it comes to connecting VPCs, customers typically choose between 2 main connectivity patterns: many-to-many or hub-and-spoke.
Many-to-many versus hub-and-spoke.
Yeah. In a many-to-many setup, each VPC connects directly to every other VPC. Imagine a spider web where every point is directly linked to every other point. This offers direct, low-latency communication paths.
Like a full mesh.
Exactly, a full mesh. The hub-and-spoke model, on the other hand, centralizes all inter-VPC traffic through a single central resource, a hub. This hub then routes traffic based on defined rules out to all the spokes, which are the individual VPCs. Think of it like a bicycle wheel, spokes radiating out from that central hub.
Okay, I see the difference.
Each model has its distinct pros and cons, and these become really apparent depending on the scale and the complexity of your cloud environment.
Let's start with VPC peering then. That's
Yeah.
pretty straightforward, right? Just connecting two VPCs directly.
VPC peering is indeed the simplest, most direct, point-to-point way to connect two VPCs. It literally creates a network connection between two VPCs as if they were on the same network, enabling full bidirectional connectivity.
Just like plugging them together?
Pretty much. A key advantage is its flexibility. You can even peer VPCs that belong to different AWS accounts or are located in different AWS regions, enabling global reach for tightly coupled applications.
Oh, well, cross-account and cross-region too. Nice.
Yeah. And a major advantage of VPC peering is its cost-effectiveness. Data transfer within the same availability zone over a peering connection is completely free.
Free is good.
Free is always good, even for cross-AZ transfers within the same region. It offers the lowest overall cost and the highest aggregate performance compared to other options for inter-VPC connectivity. So it's ideal when resources in one VPC absolutely need to communicate directly with resources in another, like maybe a staging VPC needs to hit a production database VPC.
Okay, so VPC peering sounds great for those direct, tight connections. But, I can already hear the size of network engineers thinking about scaling this thing up. Where does this simple approach start to become a serious headache?
You've absolutely hit on the Achilles heel of VPC peering. It boils down to one critical limitation. It doesn't support transitive routing.
Transitive routing. Okay, what does that mean exactly?
What that means in plain terms is if you have VPC-A peered with VPC and VPC-A is also peered with VPC-C, VPC-B cannot talk to VPC-C by routing through VPC-A.
Ah, okay. It can't hop through the middle one.
Exactly. You'd actually need a direct, separate peering connection between VPC-B and VPC-C. Now, at scale, this quickly becomes an unmanageable nightmare.
I can imagine.
If you imagine an organization with, say, 100 VPCs and you wanted to set up a full mesh peering topology where every VPC could talk to every other VPC, you're looking at a staggering 4,950 individual peering connections.
Wow, 4,950. Okay, yeah, that's not happening manually.
It's not happening. Plus, there's an AWS maximum limit of 125 active peering connections per VPC anyway. So while it's great for small numbers of VPCs, maybe less than 10, it definitely doesn't scale well for large, complex environments where you need widespread inter-VPC communication. Right. And another crucial point for hybrid architectures, your on-premises connectivity, whether it's VPN or Direct Connect, has to be made to each individual VPC if you're only using peering. Resources in one peered VPC cannot reach your on-prem networks via another peered VPC's hybrid connection.
Oof, okay, so lots of individual connections needed there too. Yeah. That certainly sounds like a management nightmare as you scale up.
Yeah.
So what's the solution for larger, more complex environments that need that widespread, efficient connectivity?
This is precisely where AWS Transit Gateway shines. It provides that much-needed hub-and-spoke design for connecting potentially thousands of VPCs and also your on-premises networks. And importantly, it does so as a fully managed service.
Fully managed, that's the key.
That's a huge advantage. You don't need to provision, manage, or maintain third-party virtual appliances, nor do you need to worry about complex VPN overlays. AWS handles all the high availability and scalability for you, abstracting away that operational burden.
Takes the load off your team.
Absolutely. You can attach all your hybrid connectivity, both VPN and direct connections, to a single transit gateway. This consolidates your organization's entire AWS routing configuration into one central place, making it significantly easier to manage and troubleshoot. Effectively, Transit Gateway transforms that sprawling, unmanageable, many-to-many mesh of peering connections into a much more streamlined and manageable hub-and-spoke model, allowing for transitive routing between all attached VPCs and your on-premises networks.
And can these transit gateways connect to each other? Like, if I have applications spanning multiple AWS regions, can a transit gateway in, say, the U.S. talk to one in Europe?
Absolutely. That's another key feature. Transit Gateway peering allows you to connect your Transit Gateway instances, not just within the same region, but crucially across multiple regions.
Okay, global reach.
Exactly. This enables seamless routing of traffic between them, effectively forming a truly global network backbone. These inter-region peering connections leverage the same underlying infrastructure as VPC peering, which means the connections are encrypted, adding an inherent layer of security.
Good to know.
And for centralized management, which is a key best practice for large organizations, it's highly recommended to place your organization's transit gateway in a dedicated network services account. You can then share it with VPCs across multiple accounts within your AWS organization using AWS Resource Access Manager or RAM.
Right, okay.
That empowers your network engineers to manage connectivity from a central point, really streamlining operations. Furthermore, Transit Gateway supports integrating SD-WAN infrastructure directly using something called Transit Gateway Connect. This provides dynamic routing via BGP and high-performance GRE tunnels, offering impressive speeds up to 20 Gbps total bandwidth per attachment. Makes it a really robust solution for hybrid cloud connectivity.
Before Transit Gateway became the standard, there was something called the Transit VPC solution, right? What was that all about, and why did people use it back then?
Yeah, the Transit VPC solution was kind of the precursor. It was an earlier hub-and-spoke model specifically designed to provide those transitive routing capabilities before Transit Gateway existed.
Okay, the OG hub and spoke.
Kind of. It typically involved a central hub VPC where customers would deploy Amazon EC2 instances running software appliances, often from third-party vendors like Cisco or Palo Alto networks. These instances would then establish VPN connections over IPsec to individual spoke VPCs, routing all the inter-VPC and hybrid traffic through that central hub.
So running your own routers on EC2, essentially.
Pretty much. Its advantages included enabling transitive routing, which was a significant leap over basic VPC peering at the time. Also, by using that third-party vendor software on the EC2 instances in the hub, organizations could leverage advanced security features like Layer 7 firewalls, IPS, IBS, maybe get a unified operational experience if they already use those vendors on-prem.
Ah, consistency.
Right. It even allowed for niche use cases like connecting an AWS GovCloud instance to a commercial region VPC. However, the critical distinction was that it was a customer-managed solution.
Meaning you had to patch it, scale it, keep it running.
Exactly. You were responsible for provisioning, maintaining, and scaling the underlying EC2 instances and that whole VPN overlay. It added significant operational overhead compared to a fully managed service like Transit Gateway. The shift to Transit Gateway was really all about abstracting away that complexity.
Makes sense. So beyond these core connectivity methods like peering and Transit Gateway, what other services help connect things privately or maybe simplify network management in a complex multi-VPC environment? It sounds like there are quite a few pieces to this puzzle.
There certainly are. One really powerful piece is AWS PrivateLink. This service provides private connectivity directly between VPCs to various AWS services and even extends to your on-premises networks.
PrivateLink, how does that work?
Yeah. Interface VPC endpoints, which are powered by PrivateLink, simplify your network architecture immensely. They allow consumers in one VPC to initiate connections to a service provider's VPC without any traffic ever traversing the public internet.
Okay, stays on the AWS backbone.
Stays completely private. And a key benefit here, a real aha moment for many, is that consumer and service provider VPCs can even have overlapping IP address ranges when using PrivateLink.
Wait, overlapping IPs, that's usually a huge problem.
It is, but PrivateLink handles it. This is a significant advantage in large, decentralized organizations where maybe IP planning wasn't perfectly coordinated from the start. It's often combined with VPC peering for direct connections or with Transit Gateway for scaled hub-and-spoke connectivity, showing how these technologies can be mixed and matched to fulfill very different use cases.
And what about sharing resources across different accounts without creating complex, full-blown network connections, almost like giving different teams access to the same underlying network segment? Is there something for that?
That's precisely where VPC sharing comes in, and it's incredibly useful. It addresses a common organizational need. You want network isolation between teams at the account level, for billing and permissions, rather than having to manage strict network isolation at the VPC level, which can become overly complex.
Okay, so sharing a VPC.
Exactly. With shared VPC, multiple AWS accounts can create their application resources, EC2 instances, Lambda functions, whatever, within shared centrally managed virtual private clouds. The VPC owner shares one or more subnets with participant accounts who can then simply deploy their resources into those predefined subnets.
Ah, so the network team manages the VPC, app teams deploy into it.
Got it. The benefits are substantial. It leads to a simplified network design with much less complexity around inter-VPC connectivity. You end up with fewer VPCs to manage overall. It allows for clearer segregation of duties between network engineers and application teams. It enables better IPv4 address utilization, which is a big deal.
Especially with IPv4 scarcity.
Right. And it can even result in lower costs because there are no data transfer charges between instances belonging to different accounts within the same availability zone in the same region.
Nice.
And while participants share IP space and network resources, you can still achieve a degree of isolation by sharing a different subnet per participant and applying network access control lists, or NACLs, for additional control.
What if different teams have created VPCs with overlapping IP address ranges, and now, unexpectedly, they need to communicate? Is that even possible? Or are you just out of luck and forced to re-architect everything? That sounds painful.
That's a very common and, frustrating challenge in large organizations, especially where teams work independently or maybe after a merger. Overlapping CIDR blocks are a big problem for direct connections like VPC peering or for services like Transit Gateway, which rely on unique IP spaces.
Right, routing gets confused.
Totally. But here's the clever part. A private NAT gateway can actually help with this.
A private NAT gateway.
It allows communication between networks with overlapping CIDRs. It's a unique capability and a significant workaround for an otherwise intractable problem. Instead of having to re-IP entire VPCs, which is a massive undertaking, you can use a private NAT gateway to translate the overlapping addresses, enabling communication.
Wow. Okay, that's a neat trick.
It is. It can also be used in scenarios where maybe your on-premises networks restrict access to only approved IP addresses. If compliance rules say you can only talk to a specific block of IPs, a private NAT gateway allows large workloads running on AWS VPCs to appear as if they are behind those allow-listed IPs, solving a critical compliance and connectivity challenge.
It really sounds like AWS is constantly evolving how we manage cloud networks. What's one of the newer, maybe more comprehensive approaches for connecting everything globally, something that aims to simplify the whole network and security posture at a very high level.
That's a great observation. AWS CloudWAN is a relatively new and powerful service designed specifically to centralize your network and security posture across your entire global infrastructure.
CloudWAN. So bigger than Transit Gateway.
It builds on Transit Gateway, but it offers a higher level of abstraction and policy control. Traditionally, you'd configure individual VPCs, connect them with transit gateways or peering, then separately connect to your on-prem networks using VPNs or Direct Connect. CloudWAN takes this a significant step further by allowing you to centralize all these networking and security constructs in a single place.
A single management plane for everything.
Pretty much. You can define network segments by policy, determining exactly who can communicate with whom. You can easily isolate sensitive production traffic from development workloads or specific on-premises networks, all governed by a single version policy document. It manages your global network through AWS Network Manager, using a core network policy to define segments, regions, and attachments like VPCs, SD-WANs, client VPNs, firewalls, data centers, everything. It's designed to significantly simplify global infrastructure, connectivity, and inspection, providing a truly unified network approach.
And for application-level networking, maybe abstracting away some of the underlying network complexity for developers, there's VPC Lattice.
Yes, exactly. Amazon VPC Lattice is a fully managed application networking service. It really focuses on connecting, monitoring, and securing services across various accounts and VPCs, but at the application layer rather than just the network layer.
So less focus on IPs and routes for the dev.
Precisely. It helps interconnect services within a logical boundary, making them much easier to manage and discover for developers. It abstracts away a lot of the underlying network complexity, allowing developers to focus on their application logic rather than intricate routing tables or firewall rules.
What are the key parts of it?
Key components include services, which are your actual application units running on instances, containers, or Lambda functions, and service networks, which are these logical boundaries that automatically enable service discovery and connectivity while applying common access and observability policies to a collection of services. It also features auth policies for request-level authentication and a service directory for a centralized view of all services. It allows developers to define routing policies for things like seamless blue-green deployments, and security is managed at both the service network and individual service levels using IAM access policies, giving very granular control.
Okay, so we've talked a lot about connecting VPCs within AWS, But for so many organizations, the reality is a hybrid environment, right? They've got both cloud and on-premises data centers. How do you securely bridge that gap and create seamless connectivity between the two worlds?
This is such a fundamental question for any enterprise navigating that cloud journey. How do you seamlessly integrate your existing, often substantial on-premises infrastructure with your expanding cloud footprint? There are really three main approaches for hybrid connectivity, each suitable for different scales and needs.
Three main ways, okay.
The one-to-one setup is the simplest, but honestly the least scalable. It involves creating a separate VPN connection or a direct connect private virtual interface, or VIF, for every single VPC that needs on-premises access. This works maybe for 5 or 10 VPCs, but it quickly becomes unwieldy at enterprise scale.
Yeah, sounds messy.
It gets messy fast. For larger needs, you look at edge consolidation. Here, you centralize your hybrid IT connectivity for multiple VPCs at a single endpoint. This is typically achieved using AWS Transit Gateway and a Direct Connect Gateway, consolidating your connections and routing logic.
Centralizing again seems like a theme.
It really is for scale. And the most advanced, most comprehensive option is full mesh hybrid consolidation using CloudWAN, which, as we just discussed, is built on Transit Gateway. This provides a truly policy-based approach to networking across multiple accounts and regions, bringing all your cloud and on-premises networks into a unified, centrally managed global network.
Direct Connect is often talked about as the go-to for serious hybrid connectivity, offering those dedicated private connections. Why is that the preferred method over just VPNs, and what are the different ways you can actually use it to bridge your on-prem environment with AWS?
You're right. While a site-to-site VPN over the internet is a great starting point for hybrid connectivity, the internet's inherent unreliability, like fluctuating latency, packet loss, potential for congestion, it just makes it less suitable for critical production traffic.
Yeah, the internet does its own thing sometimes.
It does. AWS Direct Connect provides a private, dedicated network connection between your on-premises facilities and AWS, completely bypassing the public internet. This offers several compelling benefits. It often leads to reduced data transfer costs compared to egressing data over the internet. It provides increased and much more consistent bandwidth, and it delivers a significantly more reliable and predictable network experience.
So better performance, potentially lower cost, more reliable.
Exactly. And there are distinct ways you can actually connect your on-premises data centers using Direct Connect, each with different implications for scale, cost, and the overall architecture.
Okay, what are those ways?
Well, for instance, the simplest, but again, least scalable option is creating a private virtual interface, a VIF, directly to a virtual private gateway, or a VGW, which is then attached to a single VPC. You're limited to 50 VIFs per direct connection, meaning a max of 50 VPCs, and the connectivity is restricted just to the AWS region where that direct connect location is physically located. This one-to-one mapping makes it less preferred for larger deployments.
50 VPCs max, okay.
A more flexible option, maybe for a moderate number of global VPCs, is creating a private VIF to a Direct Connect gateway. Now, this gateway is a globally available resource.
Direct Connect gateway is global.
Right. This gateway can then be associated with multiple VGWs, connecting up to 20 VPCs globally over a single private VIF. This is great for a small number of global VPCs, but it's important to remember it's primarily for north-south traffic flow, that is, traffic between on-prem and AWS, and it doesn't inherently permit VPC to VPC communication unless you implement specific routing for it.
Okay, so mainly on-prem to cloud, up to 20 DPCs.
Exactly. However, the option that truly enables scale and is widely adopted for larger enterprise environments is creating a transit VIF. This transit VIF connects to a direct connect gateway that's then associated with a transit gateway.
Transit VIF to transit gateway.
This is the simplest setup for connecting multiple VPCs at scale because a single transit VIF can connect your on-premises data center to up to 6 transit gateway instances, which in turn can connect to literally thousands of VPCs across different AWS regions and accounts.
Thousands. Wow. That's scalable.
It is. It's generally more cost-effective for high-speed connections, say over 1 Gbps, but it's important to remember you're also paying for the transit gateway attachment and data processing charges. There's also a key limit: 200 advertised prefixes from the transit gateway back to your on-premises router.
200 prefixes. Need to watch that.
Definitely. Beyond just raw connectivity, there are also options now to encrypt Direct Connect at the network layer. You can create a VPN connection to Transit Gateway over a Direct Connect public VIF for accessing public services privately, Or use private IP VPN over transit VIFs for enhanced security without relying on public IP addresses at all.
Encrypting the DX link itself.
Exactly. And for advanced SD-WAN integration, you can use high-performance GRE tunnels to transit gateway over a transit VIF via that Transit Gateway Connect feature we mentioned, offering higher bandwidth than a traditional VPN.
And beyond just connecting, what about securing those direct connections themselves? Given it's a dedicated physical link, how do you ensure the data flowing over it is protected from, say, eavesdropping on that link?
Security is always paramount, absolutely, even on a private link. Customers can use MC Security Standard or MCSec encryption, that's IEE 802.1AE, with their direct connections. This capability is available for the 10 GBPs and 100 GBPs dedicated connections at select AWS locations.
MBSec, Layer 2 encryption.
Exactly. What this means is that your data is secured right at Layer 2, providing point-to-point encryption directly on the physical link itself. It's a very fundamental layer of protection. To enable MCSec, your device must have a direct Layer 2 adjacency with the Direct Connect device, so your last-mile provider would need to confirm compatibility. But yeah, it adds a foundational hardware layer of security for the physical link, protecting against eavesdropping or tampering on that specific segment of the network.
Okay. And for maximum reliability, what are the absolute best practices for direct connect resiliency? Because even a dedicated connection can have issues. Fiber cuts happen, and downtime is incredibly costly for critical workloads.
Absolutely. Fiber cuts are a real thing. To achieve truly highly resilient connectivity, the best practice is definitely to eliminate any single point of physical location failure. That means connecting from multiple data centers on your end.
Multiple data centers, okay.
And you should also utilize more than one direct connection for redundancy, especially for your critical workloads. AWS even offers the Direct Connect Resiliency Toolkit. It's a guided wizard with different redundancy models to help you design your hybrid connectivity to meet specific service-level agreement requirements, whether you need, say, 3 nines or 4 nines of uptime.
Helps you pick the right model.
Exactly. The gold standard really is to aim for at least 2 connections at 2 different Direct Connect locations for maximum redundancy. That ideally totals 4 connections, 2 from each of your locations, terminating at 2 different AWS locations. And even with all that physical redundancy, it's still a strong recommendation to consider having a site-to-site VPN connection configured as a backup to your Direct Connect setup, providing an additional path over the public internet just in case of a major Direct Connect outage.
Belt and suspenders approach. Makes sense. I've heard about something called Direct Connect Site Link. How does that fit into the picture, and what unique problem does it solve for connecting different on-premises locations?
Direct Connect Site Link is a really interesting development that addresses a specific need. Traditionally, if you wanted to configure site-to-site links between your own on-premises network, say connecting 2 branch offices or 2 data centers directly, you typically use expensive dark fiber or maybe IPsec VPNs over the internet, or rely on third-party circuit providers using technologies like MPLS.
Right, the old ways.
SiteLink allows you to enable direct site-to-site connectivity for your on-premises locations that already terminate at an AWS Direct Connect location.
So using your existing DX connection for site-to-site.
Exactly. What's truly powerful here is that you can use your Direct Connect circuit to provide this site-to-site connectivity without having to route traffic up through your VPCs in an AWS region and back down. You essentially bypass the AWS region completely for that specific site-to-site traffic.
Keeps the traffic out of AWS for that path.
Precisely. The Direct Connect gateway learns and re-advertises the IPv4 or IPv6 prefixes directly between your on-prem routers over these SiteLink-enabled VIFs. It simplifies inter-site routing and can potentially optimize latency and costs by taking a more direct path between your own sites, leveraging the AWS backbone but not involving regional resources.
Okay, let's shift gears now to network security within the cloud itself. How do organizations typically manage outbound internet access for their applications, especially at scale? Because pretty much every application needs to talk out to the internet for something, right? Whether it's downloading updates or reaching third-party APIs.
You're absolutely right. As applications deploy, many, if not most, require some form of outbound-only internet access, maybe for downloading libraries, pulling security patches, getting OS updates, calling external APIs. For IPv4 traffic, the strongly recommended approach is using a NAT gateway over trying to run your own self-managed NAT instance on EC2.
NAT gateway over NAT instance. Why?
Because NAT gateways are a fully managed service. They offer significantly better availability, much higher bandwidth, and require far less administration effort on your part compared to running, patching, and scaling your own EC2 instance as a NAT device.
Makes sense. Less work.
Less work, more reliable. The real decision here for scaling, though, is between a decentralized and a centralized egress architecture. You could deploy a NAT gateway in every single spoke VPC, and that technically works, but this can quickly become very cost prohibitive due to the hourly charges for each NAT gateway plus the data processing fees.
Yeah, those costs add up.
They do. A much more viable and cost-reducing option for larger deployments is centralizing your NAT gateways. You create a separate egress VPC, often in a dedicated network services account, deploy your NAT gateways there, and then route all outbound internet traffic from your various spoke VPCs to these centralized NAT gateways using either Transit Gateway or CloudWAN. This consolidates egress traffic and makes it easier to apply security policies or inspect it.
So centralizing NAT gateways sounds good for cost, but what about ensuring high performance and availability for all that outbound traffic? That sounds like a potential bottleneck or single point of failure if not done right.
Good point. For high availability, you should definitely use more than one NAT gateway, ideally deploying one in each availability zone where you have workloads deployed.
One per AZ.
Right. This ensures that if one NAT gateway or its entire availability zone becomes unavailable, traffic can seamlessly flow through another NAT gateway in a different AZ, maintaining connectivity. Regarding scalability, a single NAT gateway is actually quite robust. It supports up to 55,000 simultaneous connections per assigned elastic IP address and automatically scales its bandwidth from a baseline of 5 Gbps up to a bursting capacity of 100 Gbps.
100 Gbps burst. Wow.
Yeah, it's pretty beefy. It's important to note, however, that Transit Gateway generally doesn't load balance traffic evenly across NAT gateways and multiple AZs in the way a traditional load balancer would. Traffic typically prefers to stay within the same availability zone if possible to minimize those cross-AZ data transfer costs and latency.
AZ affinity.
Exactly. In terms of security for this centralized setup, you can manage access using security groups on the source instances back in the spoke VPCs. You can implement black hole routes in the Transit Gateway route tables to specifically block unwanted destinations. And you can apply network ACLs on the NAT gateway's public subnet in the egress VPC to finally control which specific IP addresses or ports are allowed or blocked.
And what about IPv6 egress? Is it handled similarly to IPv4 with NAT gateways, or are there different patterns for it?
It's a bit different for IPv6 egress in dual-stack deployments. You primarily have two patterns. You can go with a decentralized approach where you deploy egress-only internet gateways in each spoke VPC.
Egress-only internet gateways.
Yeah, these are specific to IPv6. They are horizontally scaled, inherently redundant, highly available, and crucially, they're completely free to use. They allow outbound IPv6 communication from your instances, while importantly preventing any internet-initiated IPv6 connections into your VPC, maintaining security.
Free and secure outbound.
Nice. It's a great option. Or, for scenarios where you need centralized traffic inspection for your IPv6 outbound traffic, you can choose a centralized IPv6 egress pattern. Here, all IPv6 traffic is sent to a dedicated centralized VPC. This can be achieved using techniques like IPv6 to IPv6 network prefix translation, or NPTV6, perhaps using NT66 instances along with NAT gateways, or by employing proxy instances fronted by a network load balancer in that central VPC to manage the outbound flow.
Okay, moving from outbound to inbound traffic and also internal traffic, what about centralizing network security for traffic flowing between VPCs? Or maybe from on-premises to VPCs. It seems like inspecting every single packet everywhere would get incredibly expensive and complex very quickly.
You've hit on a key challenge there. Many organizations absolutely want to implement Layer 367 firewalls or intrusion prevention systems, IPS, or intrusion detection systems, IDS, within their multi-account environments. They want to inspect that east-west traffic, the VPC to VPC communication, or the north-south traffic coming from on-premises into the VPCs.
Right, need that visibility.
But to reduce costs and manageability, it's indeed highly beneficial to be selective about what traffic actually gets inspected. This leads to the crucial concept of security zones.
Security zones, like trust levels.
Exactly. You might define zones like untrusted, maybe for third-party connections, or sandbox VPCs, production, development, and a dedicated security zone where your firewall components or inspection services actually reside. You then use multiple route tables and strategic black hole routes within your transit gateway configuration to enforce security isolation and carefully control the traffic flow between these zones. This allows for really fine-grained control and helps significantly reduce costs by not inspecting every single packet, but rather focusing inspection only on traffic that traverses these defined trust boundaries.
How does AWS Network Firewall fit into this centralized security model? It's a managed service, so it sounds like it could simplify things considerably compared to rolling your own firewalls.
It definitely can. AWS Network Firewall is a stateful, fully managed network firewall service that integrates very seamlessly into a centralized architecture, particularly when you're using Transit Gateway. In this model, you deploy network firewall endpoints in multiple availability zones within your dedicated security VPC, ideally. One endpoint in each AZ where you have workloads. Again, one per AZ for high availability. Right. These endpoints then become a default route table target for all the traffic that you want to inspect as it moves through the transit gateway. What's absolutely crucial here for stateful inspection is enabling appliance mode on the transit gateway attachment to the firewall VPC.
Appliance mode, what does that do?
It ensures that bidirectional traffic for a given flow is routed symmetrically. That means it goes through the exact same firewall appliance endpoint and availability zone for the entire life of the connection. This is essential for stateful firewalls that perform deep packet inspection because they need to see both sides of the conversation to maintain the connection state.
Ah, okay. Keeps the conversation together for the firewall.
Exactly. AWS Network Firewall automatically scales its capacity up or down based on traffic load, providing impressive throughput of up to 100 GBPs per availability zone, and it supports advanced Suricata rules for deeper customizable inspection. An important nuance is that it doesn't perform network address translation, NET itself. That function is typically handled by a separate NET gateway after the inspection happens, which allows the firewall to see the original source IP address for better logging and policy enforcement.
What if an organization already has a preferred third-party virtual appliance for security inspection? Maybe something they've invested heavily in and want to continue using in the cloud. How do they integrate that into a centralized inspection model?
That's a very common scenario, and this is where the Gateway Load Balancer, or GWLB, comes into play, especially when paired with Transit Gateway. Gateway Load Balancer is a managed service that makes it incredibly easy to deploy, scale, and manage those very third-party virtual appliances, things like next-generation firewalls, intrusion prevention systems, or other specialized security solutions.
So GWLB manages the third-party boxes.
It manages the insertion and scaling of traffic to them. You deploy the Gateway Load Balancer itself and your fleet of virtual appliances within a separate, dedicated security VPC. The GWLB then exposes Gateway Load Balancer endpoints, or GWLBEs, which become routable targets in other VPCs. This allows you to route traffic from your transit gateway directly to your fleet of virtual appliances for inspection.
Okay, so traffic goes GWLBE to TWLB, BETW by FAE, appliance must UWLAB each.
Exactly. And again, appliance mode on the transit gateway attachment is key here to maintain that flow symmetry, ensuring both directions of a traffic flow pass through the same firewall instance. A huge advantage is that GWLB can use auto-scaling groups as targets for your virtual appliances. This takes away the heavy lifting of managing the availability and scalability of your appliance fleet yourself.
Ah, auto-scaling for firewalls. That's huge.
It is. It also leverages AWS PrivateLink for secure traffic exchange across VPC boundaries without traversing the public internet, and it can even expose a stack of firewalls as a firewall as a service, or FWAS endpoint, for other accounts within your organization to consume easily.
So just to recap these two main centralized security options, what's the core difference between choosing AWS Network Firewall versus using Gateway Load Balancer with third-party appliances? It sounds like they achieve similar goals, but in fundamentally different ways.
That's a critical distinction for decision makers when they're designing their security architecture. AWS Network Firewall is a fully managed network firewall that includes built-in IDS and IPS capabilities, and it's compatible with the widely used Suricata rules engine. The key here is managed. AWS handles its scalability and availability automatically, making it generally simpler to deploy and manage from an operational perspective. It's often more cost-effective if its native capabilities meet your organization's specific security requirements.
Okay, network firewall, simpler, managed, maybe cheaper if it fits.
Right. Gateway Load Balancer, on the other hand, is also a managed service, but its primary purpose is to facilitate the deployment and scaling of third-party virtual appliances. While AWS manages the GWLB service itself, you, as the customer, are still responsible for managing the scaling and availability of the virtual appliances running behind it, patching them, licensing them, etc.
So GWLB will more flexibility for specific vendors, but you manage the appliances.
Exactly. GWLB offers superior flexibility if you need specific vendor functionality, maybe a particular user interface you're already familiar with, or advanced Layer 7 inspection capabilities that might not be covered by network firewall's native offerings. Both services offer similar high-scale supporting up to 100 GBPs per endpoint in an availability zone, but their cost structures and management responsibilities differ significantly.
Let's talk about protecting internet-facing applications now. These are, by their nature, directly exposed to all sorts of threats from the public internet. How do you handle centralized inbound inspection and protect against common attacks like SQL injection or cross-site scripting?
Internet-facing applications inherently have a much larger attack surface, so robust protection is absolutely non-negotiable. You can secure these workloads in several ways, often using a layered approach. AWS Web Application Firewall, or WAF, is an excellent first line of defense for inspecting inbound web traffic from the internet.
Wife at the edge.
Exactly. It's especially good for HTTP header inspection and protecting against common web exploits and bots, things like SQL injection, cross-site scripting, or credential stuffing attacks. WAF integrates seamlessly with application load balancers, ALBs, API gateway, and CloudFront distributions, letting you apply rules right at the edge before traffic even hits your application servers.
And can you manage WAF centrally?
Yes. For centralized management across multiple accounts in an AWS organization, you can use AWS Firewall Manager. This allows you to automatically apply WAF rules, including AWS managed rules for common threats like the OWASP Top 10, across your entire application footprint consistently. WAF is a fully managed service, meaning no appliances are needed, and it provides near real-time logs for immediate visibility into potential threats.
Okay, WAF is key for web apps. What about other options for inbound inspection?
Alternatively, if you need more advanced inspection or perhaps prefer specific vendor capabilities, you can centralize inbound inspection with third-party firewall appliances deployed on EC2 instances behind an elastic load balancer in a dedicated inspection VPC. This allows for those advanced inspection capabilities offered by those third-party solutions.
Running third-party firewalls for inbound too.
Right. Or you can use the gateway load balancer model again. You deploy GWLB endpoints in an edge VPC, the one facing the internet, and route inbound traffic from the internet through your next-generation firewalls, which are sitting behind the GWLB in a centralized appliance VPC. This also allows for auto-scaling of your inbound security layer.
GWLB for inbound as well. Flexible.
Very. And for using AWS Network Firewall in a centralized ingress architecture, it inspects traffic right as it enters the edge VPC, which can be a very cost-effective deployment model. It can even perform deep packet inspection, or DPI, by decrypting traffic using TLS certificates, inspecting the payload, and then re-encrypting it before sending it on. This offers a very thorough level of scrutiny, even for encrypted traffic.
Load balancers aren't just for distributing traffic evenly, are they? You mentioned WAF integration, but they also play a critical role in DDoS resiliency, acting as a kind of shield for your applications, right?
That's a key point that's often overlooked when people just think of load balancers for scaling. Elastic load balancing, or ELB, serves as a vital first line of defense against large distributed denial of service or DDoS attacks.
How do they help with DDoS?
By automatically distributing incoming traffic across multiple back-end instances, ELB significantly reduces the risk of overwhelming any single Amazon EC2 instance. The different ELB types contribute in distinct ways. The Application Load Balancer, ALB, specifically designed for web applications, can inherently absorb and block many common Layer 7 DDoS attacks like HTTP floods, and it automatically scales to handle the additional malicious traffic when these types of attacks are detected, often without even affecting your bill.
So ALB handles web attacks well. What about other types?
For non-HTTP HTTPS applications, you'd typically use the Network Load Balancer, NLB, which routes traffic with ultra-low latency at Layer 4. While NLB typically passes all valid TCP, SYN, or UDP traffic directly to targets, for TCP listeners, you'd ideally want to deploy AWS Global Accelerator in front of it for comprehensive protection against things like TCP, SYN floods. Additionally, AWS Shield Advanced, the paid DDoS protection service, can be configured with elastic IP addresses assigned to the network load balancer to apply relevant, more advanced DDoS mitigations. It's really about designing for resilience from the ground up, with load balancing as a core component of your defense strategy.
I've heard about security group connection tracking issues related to DDoS. What's that about, and how can it impact your application's ability to handle an attack if you're not careful?
Ah, yes. This brings up a subtle but really critical configuration detail for optimizing your security groups for DDoS resilience. Normally, security groups use connection tracking to automatically allow response traffic back out when an inbound rule is very broad, for example, allowing traffic in from 0.0.00, meaning from anywhere on the internet, but you haven't configured an explicit outbound rule for the response. The security group effectively remembers the connection state to allow the return traffic.
Oh, it tracks the connections.
Right. However, in the event of a high-volume DDoS attack, the maximum number of connections that a security group can track can actually be exhausted. When this limit is reached, it can prevent new legitimate connections from being established, even if your underlying instances and load balancer are perfectly healthy and capable of handling more load.
So the security group becomes the bottleneck. How do you fix that?
To avoid this and improve DDoS resilience for your public-facing application load balancers or classic load balancers, you should configure your security group with explicit inbound and outbound rules. For example, allow all inbound TCP from 0.0.00 on your application port, and crucially, also allow all outbound TCP to 0.0.0.00 on all ports, or ephemeral ports. This ensures that response traffic is allowed by the explicit outbound rule itself, not by relying on connection tracking. This enables the load balancer to scale effectively based on traffic increase during an attack without hitting those connection tracking limits. It's a small detail, but vital for resilience.
Okay, let's zoom out beyond the cloud now and talk about the broader internet itself. What exactly is internet peering, and why is it so important for the global flow of data? Sounds like something big ISPs do.
It is something big ISPs do, but also large content providers, cloud providers, enterprises, anyone moving significant amounts of traffic. Internet peering is essentially the direct interconnection of two independent internet networks. Technical term is autonomous systems, or ASN specifically, to exchange traffic between their networks and customers.
So bypassing the middleman.
Exactly. Instead of paying a third-party transit provider like a major global telecom company to carry your traffic across the global internet to reach another specific network, you're directly exchanging traffic with that other network at a mutually agreed upon point, usually an internet exchange point or a private facility.
Well, why bother? What are the benefits?
The main reasons to peer are incredibly compelling for large network operators. First, there's potentially significant cost reduction by avoiding those transit fees for traffic that can be exchanged directly with the destination network. Second, it often leads to a performance increase due to short-circuiting the traffic path, meaning fewer network hops and lower latency, as the data doesn't have to traverse multiple intermediary transit networks. And third, it provides increased resiliency by having multiple points of interconnection to various providers and peers, diversifying your network paths and reducing reliance on any single transit provider. So while transit providers give you global reachability, direct peering optimizes traffic flow specifically between the two interconnected networks for efficiency, cost, and performance.
How do networks actually influence where their traffic goes, especially when they're peering with lots of others? It sounds like there must be a lot of strategic maneuvering happening behind the scenes with routing protocols.
You're absolutely right. There is a delicate and complex dance of traffic control using the Border Gateway Protocol, or BGP. Networks use various BGP attributes to influence how traffic routes. For inbound traffic, that's traffic coming to your network from a peer, you can influence its path selection by doing things like selectively suppressing your prefix advertisements to certain peers, essentially making your routes less visible or attractive for certain traffic. Or you can advertise longer, more specific prefixes, which are generally preferred by BGP's path selection algorithm.
Where specific routes win.
Right. You can also manipulate attributes like the multi-exit discriminator or MED and the AS path length, as path length is particularly influential. A shorter path is generally preferred by BGP. So a network might prepend its own AS number multiple times when advertising to a peer to make its path appear artificially longer and thus less desirable for certain inbound traffic, subtly steering that traffic away from that specific peering link.
Clever tricks. What about outbound traffic?
For outbound traffic, that's traffic originating from your network and heading out to the internet, you primarily use the local preference attribute within your own network. Local preference is the highest priority BGP attribute for path selection within your own autonomous system. You set higher local preference values on routes learned from peers or transit providers that you prefer your outbound traffic to take. MED can also play a role in influencing your exit point if multiple links exist to the same neighboring AS. And increasingly, networks use more advanced traffic engineering methods like segment routing traffic engineering, SRTE, to explicitly steer specific types of traffic to specific locations or peers based on defined criteria like latency targets, cost objectives, or even current link utilization.
I've heard the terms hot potato and cold potato routing thrown around in this context. What do those interesting metaphors actually mean in the world of internet routing?
Yeah, they're classic metaphors in internet routing that describe a network's fundamental strategy for handing off traffic to other networks. Hot potato routing means your network tries to offload traffic to a peer or transit provider as quickly and as close to the origin as possible, routing it to the nearest interconnection point available. Imagine literally throwing a hot potato. You want to get rid of it fast.
Get it off your network ASAP.
Exactly. This approach is typically used by peering partners when exchanging traffic with each other because it minimizes their own network's transport costs. They want to avoid carrying traffic across their expensive backbone if they can hand it off sooner to the peer.
Makes sense for peers.
Yeah.
What's cold potato?
Cold potato routing, on the other hand, means your network carries the traffic further across its own backbone, trying to bring it as close as possible to its final destination within your network before handing it off to another network, maybe a peer or a downstream customer. Think of holding a cold potato. You're comfortable carrying it for a while longer. Transit providers, who you pay to carry your traffic across the global internet, typically use cold potato routing. They want to control the path, maintain quality, and optimize it for their paying customers, whereas direct peers will generally use hot potato to minimize their own costs. It's a strategic decision based on balancing cost control and performance guarantees.
With all this complexity in these strategic routing decisions, how do networks actually get visibility into what's happening on their highly distributed systems? How do they plan for future growth and potential failures?
That's where network telemetry becomes absolutely critical. You can't manage what you can't measure, right? Modern networks rely on advanced tools and protocols to gain deep insights into their operation. For instance, there's Cisco Model-Driven Telemetry, or MDT, which streams fine-grained time series data like interface statistics, router CPU utilization, queue depths directly from network devices in a structured way, providing optimized and granular data collection compared to older methods like SNMP polling.
So, real-time stats from the devices.
Exactly. There's also BGP Monitoring Protocol, or BMP. This gives you an exact copy of BGP messages, updates, withdrawals, session status, along with their context, directly from the router's BGP processes. This is invaluable for monitoring pierceability, detecting bad or anomalous BGP attributes like invalid ASNs, and performing firmware analysis of routing events after something goes wrong.
Seeing the actual BGP messages. Powerful.
Very. Then there's NetFlow, or its standardized version, IPFAX. This collects information about actual traffic flows traversing the network, detailing who's talking to whom, which applications are being used, and how much data is being exchanged between different points. When you combine this flow information with the BGP routing data, it allows for incredibly deep capacity planning use cases.
Like seeing where the traffic is actually going.
Precisely. You can derive detailed traffic matrices, develop network growth models based on historical traffic patterns, and even simulate network failures like what happens if this major peering link goes down, to balance cost against consumer experience and service level agreements. For example, by analyzing NetFlow data from a major interconnection point like Ashburn, Virginia, you might discover huge volumes of traffic going to YouTube and Netflix that is ultimately destined for users in Boston. This data might strongly suggest that you should establish direct peering relationships in Boston with those specific content providers to improve performance for your Boston users and reduce your transit costs out of Ashburn. Tools like Cisco Crosswork Cloud can provide global BGP visibility and actionable network insights by aggregating and analyzing this kind of telemetry data.
Internet peering sounds great for cost and performance, definitely. But it also sounds like a pretty significant attack surface, given how interconnected and, frankly, trusting everything seems to be. What are the major security concerns that network operators face in this peering environment?
You're absolutely right to bring that up. Securing something so inherently open and distributed as the internet's peering fabric is a massive and ongoing challenge. Peering security events are a very real concern, and they can have widespread, devastating impacts. One major threat is BGP route hijacks. This is where malicious actors deliberately advertise IP prefixes they don't legitimately own, trying to redirect traffic destined for those prefixes to their own network, maybe to intercept it, analyze it, or just drop it.
Stealing internet traffic routes.
Essentially, yes. Another common issue is route leaks. This is usually unintentional, where a network mistakenly advertises prefixes learned from one peer or transit provider to another peer or transit provider, violating routing policy and causing traffic to take suboptimal or incorrect paths across the internet. This can lead to widespread outages or severe performance degradation.
Accidental misdirection.
Right. And of course, DDoS attacks are a constant and escalating threat, with millions of volumetric and application layer attacks occurring annually against internet-facing services, often leveraging peered connections. The Cloudflare 1.1 BGP hijack and subsequent route leak incident back in 2024 is a prime example of how these BGP issues can impact critical, widespread services and millions of users globally. Beyond these headline issues, the daily challenges also include constant automated scanning for vulnerabilities, the pervasive presence of botnet command and control traffic trying to hide, and spoofed source IP traffic hitting your peering edge, all of which require constant vigilance and mitigation.
So given all those threats, how are networks mitigating them at the peering edge? What are the key strategies and technologies being employed today to try to protect the internet's underlying routing fabric?
There are several crucial mitigation strategies, often layered together because no single solution is foolproof. For DDoS attacks, BGP FlowSpec is an increasingly powerful tool. It uses multi-protocol BGP, MPBGP extensions to distribute ingress data plane filtering rules dynamically across your network edge routers. This allows you to match on specific packet criteria like source destination IP, ports, packet length, protocol, and then apply actions like dropping the traffic, rate limiting, policing it, redirecting it to a scrubbing center, or just marking it. This provides scalable, distributed DDoS protection right at the network edge where the attack traffic enters.
FlowSpec for DDoS. Got it.
Okay.
What about securing BGP itself?
To secure the BGP sessions themselves between peering routers, TCP authentication option, or TCP/AO, defined in RFC 5925, is now widely recommended over the older, weaker MD5 option. TCP/AO uses strong cryptographic hash algorithms like HMSE SHA-256 to authenticate every TCP segment within the BGP session. This protects against critical session threats like TCP/RST attacks, session hijacking or snooping, and even SYN floods targeting the BGP port, which is especially important as peering carries increasingly critical application traffic.
Stronger session security with TCP/AO.
Okay. Then there's a major ongoing global effort to enhance route security, ensuring the routing information itself is valid. Resource Public Key Infrastructure, or RPKI, coupled with Route Origin Validation, or ROV, allows network operators to cryptographically validate that the autonomous system claiming to originate a given IP prefix in a BGP update is actually authorized to do so by the legitimate holder of that IP space. This helps prevent many types of BGP hijacks.
RPKI checks the origin AS. What about leaks?
RPKI helps with origin validation, but leaks often involve incorrect AS paths after the origin. For that, there's AS Provider Authorization, or ASPA. This is a newer RPKI-signed object where a customer AS, or any AS, can attest which ASNs are its legitimate upstream transit providers. Routers can then use this information to validate the AS path and received BGP updates, helping to detect invalid ASNs appearing in the middle of a path, which is a common indicator of a route leak.
ASPA checks the path.
Yes. And beyond these protocol-level solutions, networks implement strict BGP route filtering on all peer connections based on agreed policies, often using tools like Internet Routing Registries, IRRs. They use ACE path filtering to ensure transit providers are only used for transit traffic, not for learning routes back from customers or peers. Ideally, these filters are automated for quick deployment and updates. At the data plane boundary, edge routers filter obviously bogus traffic like packets sourced from private or unallocated IP space, BCP38, block known malicious control plane traffic, drop packets to well-known bad ports like Chargen, consider applying rate limiting to certain traffic types, and some even route unused dark space IP addresses to honeypot servers to collect threat intelligence. It's truly a multi-layered defense-in-depth approach needed to secure the internet's peering ecosystem.
Let's swing back to the cloud environment, specifically AWS. DNS is often an unsung hero of the internet, right? But it's absolutely critical for any network infrastructure, especially hybrid ones. It enables everything from web browsing to internal service discovery. How do we manage DNS effectively in these complex cloud environments, ensuring both reliable resolution and security?
DNS is indeed a critical foundational component. It provides that essential hostname to IP address resolution that virtually all applications rely on to find each other. In AWS, when you launch an EC2 instance, it automatically gets a private DNS hostname resolved by the default Route 53 resolver service within its VPC.
Okay, internal AWS resolution is handled. What about hybrid?
The trick is how you integrate this internal AWS DNS with your existing on-premises DNS infrastructure. Since the native Route 53 resolver service isn't directly reachable from your on-premises networks over VPN or Direct Connect, you need to deploy specific Route 53 resolver inbound and outbound endpoints.
Inbound and outbound endpoints. What do they do?
An inbound endpoint essentially provides an IP address within your VPC that your on-premises DNS servers can forward queries to. It receives DNS queries that you forward to your VPCs from on-premises, allowing your on-prem servers and clients to successfully resolve AWS resource domain names, like those for your EC2 instances or records in your Route 53 private hosted zones.
So on-prem can resolve cloud names.
Right. Conversely, an outbound endpoint does the opposite. It forwards DNS queries originating from your VPCs out to your on-premises DNS servers or any external DNS server you configure. This enables resources running in the cloud to resolve your internal corporate hostname stored in your on-prem DNS.
And cloud can resolve on-prem names. Got it. Where should these endpoints live?
For manageability and cost efficiency, it's definitely not recommended to create these inbound and outbound endpoints in every single VPC. That would get expensive and complex fast. Instead, the best practice is to centralize them. Deploy them in a dedicated VPC, typically within your shared network services account, and then associate them with or share them across your entire AWS landing zone or organization. This allows for much better central control, simplifies management, and significantly reduces the cumulative hourly charges you'd incur from having dozens or hundreds of distributed endpoints.
Centralize again. Okay. And what about DNS security? With DNS being such a fundamental service, it seems like a prime target for attacks or maybe even data exfiltration attempts.
That's a crucial point.
Yeah?
How do you secure your DNS traffic itself, especially given its pervasive nature? Amazon Route 53 Resolver DNS Firewall is a service designed to help you filter and regulate outbound DNS traffic, specifically originating from your VPCs, adding a crucial layer of security at the DNS resolution step.
DNS a firewall. What can it block?
A primary use case for the DNS firewall is to prevent data exfiltration over DNS. It does this by allowing resources within your VPCs to make outbound DNS requests only for domains that your organization explicitly trusts. You essentially create and enforce an allow list of approved domains.
Only talk to approved domains.
Exactly. Conversely, you can also create block lists for domains you absolutely don't want your resources communicating with perhaps known malware, command and control domains, phishing sites, or other suspicious destinations identified by threat intelligence feeds. You can define rules with various actions like no data, which returns an empty answer for a query, override, which provides a custom response, maybe pointing to an internal sinkhole, or NX domain, which tells the client the domain doesn't exist. You can even set up alerts to monitor rule activity in a dry run mode before pushing them live to production. This proactive filtering adds a crucial layer of security, protecting against command and control communication, DNS tunneling for exfiltration, and other malicious activities that use the DNS protocol.
Finally, let's talk about connecting to AWS services themselves, things like S3, DynamoDB, SQS privately, without the traffic ever touching the public internet. This sounds incredibly useful for security and maybe even performance.
That's precisely the power of VPC endpoints. A VPC endpoint allows you to privately connect your VPC directly to supported AWS services like Amazon S3 or Amazon DynamoDB, or even to your own custom services that you've exposed via AWS PrivateLink, all without requiring an internet gateway, a NAT device, a VPN connection, or even an AWS Direct connection for that specific service traffic.
So no internet path needed at all.
None at all for that service connection. This is hugely beneficial because your VPC is not exposed to the public internet for that communication, and all the traffic stays entirely on the secure, high-speed AWS global network backbone.
What types of endpoints are there?
There are two main types. First, there are gateway endpoints. These are specifically for connecting to Amazon S3 and Amazon DynamoDB within the same region, and they come with no additional hourly charge, which is great. They work by adding entries to your VPC's route table.
Gateway endpoints for S3 and DynamoDB. Free. Okay.
A second, there are interface endpoints. These are powered by AWS PrivateLink and are used for a much wider range of AWS services like SQS, Kinesis, Systems Manager, etc. And also for accessing your own services or third-party SaaS services hosted on AWS via PrivateLink. Interface endpoints work by placing an elastic network interface, ENI, with a private IP address from your VPC subnet directly into your VPC.
Interface endpoints for everything else. Uses PrivateLink. Got it. Do I need one in every VPC?
By default, you might think you need to create an interface endpoint in every single VPC that needs access to a particular service, but they can quickly become cost-prohibitive at scale due to the hourly charges for each interface endpoint ENI. A powerful best practice, again leaning towards centralization, is to centralize these interface endpoints in a dedicated VPC, typically within your network services account. Then have all your other Smoke VPCs access these centralized endpoints via your transit gateway.
Centralized endpoints access via TGW. How does DNS work for that?
Good question. This requires a bit of manual DNS configuration. You typically use a Route 53 private hosted zone associated with all your Spoke VPCs. In that zone, you create alias records that resolve the public AWS service endpoints, like s3.useast1.amazonos.com, to the private IP addresses of your centralized interface endpoints in the network services VPC. This way, when an instance in a Spoke VPC tries to reach S3, DNS resolves it to the private IP of the central endpoint, and Transit Gateway routes the traffic there. It greatly simplifies management and reduces costs significantly. Plus, these centralized endpoints are also accessible from your on-premises networks over VPN and Direct Connect, further unifying your hybrid connectivity and providing consistent private access to AWS services from everywhere.
And can these private endpoint connections extend across different AWS regions? So if I have an application in, say, US East 1 that needs to talk privately to a service endpoint centralized in US West 2, can it do that without traversing the public internet?
Yes, absolutely they can. When you have multiple VPCs across different AWS regions that need to share access to a common VPC endpoint, which itself resides in one specific region, you achieve this using that Route 53 private hosted zone concept again. But this time, associate the private hosted zone with VPCs in both regions. You'd have an alias record in the zone pointing to the regional endpoint.
So DNS works cross-region. How does the traffic get there?
To route the actual traffic between the VPCs in this multi-region architecture, the transit gateways in each region need to be peered together using transit gateway inter-region peering. This means that an EC2 instance in, say, US West 1 can use the shared private hosted zone to get the private IP address of an interface endpoint located in US West 2, and then the traffic gets routed securely over the transit gateway peering connection between the two regions.
TGW peering handles the cross-region path.
Exactly. The key benefit is that the traffic remains entirely within the AWS global network backbone, providing secure, private cross-region access to those services. It's important to remember, though, that standard inter-region data transfer charges do still apply for traffic flowing over that TGW peering connection.
Okay, one last area. Beyond infrastructure connectivity, how do organizations provide secure access to applications for users, especially when those applications are running in private networks, but without relying on traditional VPNs, which can often be cumbersome for end users and maybe not granular enough?
That's a truly important question about modern access strategies, moving towards zero-trust principles for the distributed workforce. AWS Verified Access is a service specifically designed to deliver secure access to your internal web applications running in private networks without requiring a traditional VPN client on the user's device.
No VPN, how does that work?
It functions essentially as an identity-aware reverse proxy. It sits in front of your private applications and evaluates every single incoming request in real time based on a multitude of factors before granting access. These factors include the user's identity, verified via your identity provider like Okta or Azure AD, the security posture of their device, is it compliant, is the OS patched, is endpoint security running, and even contextual information like their geographic location.
Checks identity and device health for every request.
Every single request. It's a policy-driven service, meaning access is granted only if all your predefined security requirements are met for that specific user, device, and context at that moment in time. The key components include verified access instances that actually evaluate the incoming requests, verified access endpoints, which represent your backend applications. These can be network load balancers, application load balancers, or even just individual ENIs. Verified access groups to logically categorize endpoints that share similar security requirements, and of course, access policies, which are your user-defined roles written in the CEDAR policy language.
CEDAR policy language, okay.
It also integrates seamlessly with various trust providers. These are sources for the user identity information, like your IDP, and the device security state, like CrowdStrike or Jamf. This ensures that crucial trust data, like a user's email address, their group memberships, or whether their device has malware protection enabled, is evaluated against your access policies for every single application request. This truly enhances an organization's security posture by enforcing granular, context-aware access at the application layer, moving away from the old model of just trusting anyone inside the VPN perimeter.
Wow. Okay. We've covered a massive amount of ground today, from specific AWS services like Transit Gateway and PrivateLink to intricate internet routing concepts like BGP and peering security. Stepping back one last time, what would you say are some of the universal core challenges in cloud networking that organizations face, regardless of the specific service they're using, and what are the overarching solutions to those persistent issues? Yeah, it's good to zoom out. Many challenges are indeed common across different cloud environments, whether you're primarily on AWS, Azure, or Google Cloud. One is undeniably network performance and latency. Cloud applications need to be fast and responsive. The solution involves a combination of optimizing routing, using techniques like anycast routing to direct users to the nearest possible data center, leveraging content delivery networks, CDNs, extensively to cache static and dynamic content closer to the end users, and sometimes implementing quality of service, QoS mechanisms, where possible, to prioritize critical application traffic, ensuring responsiveness even when the network is busy.
Performance is key. What else?
Another huge and ever-present concern is security and compliance. The cloud's shared responsibility model means you, the customer, are always responsible for securing your data and applications in the cloud. Here, adopting a zero-trust security model, which fundamentally means never trust, always verify, continuously validating every request regardless of its origin, is becoming essential. Using end-to-end encryption for all data, both in transit over the network and at rest on storage, is paramount. And conducting regular security audits, vulnerability scanning, and compliance checks against relevant standards like PCI DSS, Hyper-TOW, SOC2 is absolutely necessary. It's about building security in at every layer and continuously validating it.
And what about as organizations inevitably expand to use multiple cloud providers, maybe to avoid vendor lock-in or leverage specific strengths of each platform? How do they manage the networking complexities of these multi-cloud environments?
Managing multi-cloud environments definitely introduces unique networking complexities. The solution often lies in using unified infrastructure as code tools like Terraform or Ansible to try and achieve consistent network configurations and policies across different cloud providers. Implementing cross-cloud connectivity solutions, such as using AWS Transit Gateway, paired with Azure Virtual WAN, or connected to Google Cloud's Interconnect, becomes critical for building efficient and secure connections between these disparate environments. And deploying centralized monitoring and observability solutions that can ingest data from all clouds is vital to gain comprehensive visibility across all your cloud networks, providing that elusive single pane of glass.
Makes sense. And cost management. Cloud networking costs, especially data transfer, can sneak up on you.
Oh, absolutely. Cloud networking costs can quickly get out of hand if not managed proactively. Key solutions include diligently using the cost management tools provided by the cloud platforms themselves to monitor, analyze, and forecast spending trends. Optimizing data transfer is huge, designing architectures that keep frequently communicating components within the same region or even the same availability zone where possible, or using direct interconnects instead of the public internet for high-volume transfers between clouds or to on-prem. And regularly right-sizing network resources like load balancers, NAT gateways, VPN connections to avoid over-provisioning and paying for capacity you don't actually need.
And for applications that need to grow or shrink really quickly based on demand, how do you build a network that truly embraces that cloud promise of scalability and flexibility?
Scalability and flexibility are indeed core cloud promises, but also significant challenges to implement correctly from a networking perspective. Here, the solution involves deeply leveraging the cloud-native auto-scaling features for network components like load balancers and gateway fleets to dynamically adjust resources based on real-time demand, ensuring optimal performance without manual intervention. Designing applications using a microservices architecture is also key from a network scaling perspective, as it allows individual components and their associated network resources to scale independently based on their specific load. And of course, robust, intelligent load balancing is fundamental to efficiently distribute incoming traffic across scaled-out instances or containers to prevent bottlenecks and ensure optimal performance as your business grows or experiences traffic spikes.
One last one. Network visibility and monitoring. It can be tricky with all the abstraction in the cloud.
Definitely. Visibility can be a challenge because much of the underlying physical infrastructure is hidden from you. The solution is to leverage the rich set of cloud-native monitoring tools provided by the platforms like AWS CloudWatch, Azure Monitor, or Google Cloud Monitoring. Enabling detailed network flow logs, like VPC flow logs in AWS, is crucial to capture metadata about all the IP traffic flowing through your cloud networks, which is invaluable for security analysis, anomaly detection, and troubleshooting connectivity issues. And increasingly, organizations are using AI and machine learning-powered observability tools that can ingest all of this telemetry data and provide actionable insights that might otherwise be buried in mountains of logs. Oh, and for integration with legacy systems, which is a reality for most established enterprises, hybrid cloud connectivity solutions using VPNs or Direct Connect, leveraging APIs and middleware platforms to bridge communication gaps, and careful network segmentation to isolate legacy systems while enabling necessary secure access are all key components of a successful hybrid IT strategy.
Wow, what a truly deep dive into the foundational elements of modern cloud and internet networking. We've seriously unpacked everything from how organizations should segment and manage their cloud environments using multi-account strategies and tools like IPAM, all the way to the intricate ways virtual private clouds connect, whether that's through the deceptive simplicity of VPC peering or the vast scalability offered by Transit Gateway, CloudWAN, and PrivateLink.
Yeah, and we explored that critical bridge between the cloud and on-premises data centers using AWS Direct Connect and all its different flavors, VIFs, gateways, transit VIFs, while also emphasizing the importance of security with things like MACsec encryption and the best practices for building resilient, highly available connections.
Absolutely. And we didn't stop there. We delved deep into the crucial aspects of network security within the cloud, from centralizing internet egress safely and cost-effectively with NAT gateways to implementing robust inspection architectures using AWS Network Firewall or Gateway Load Balancer with third-party appliances for both inbound and outbound traffic. We explored how load balancers are actually fundamental to DDoS resiliency.
And then we took that fascinating journey into the world of internet peering, covering BGP routing strategies like hot and cold potato and highlighting the critical security measures needed there like BGP FlowSpec, TCP/AO for session security, and the vital role of RPKI and ASPA in combating route hijacks and leaks.
Right. And finally, we tied it all together by looking at the often overlooked but critical nuances of hybrid DNS management with Route 53 resolver endpoints and DNS firewall, and securing access down to the application level for users with services like verified access, moving beyond traditional VPNs.
Yeah, the sheer breadth of options and considerations we've discussed really highlights that there's rarely a single right answer in cloud networking. It's much more about understanding the spectrum of powerful tools and solutions and choosing the right combination to fit your specific technical requirements, security posture, operational capabilities, and of course, budget.
So what does this all mean for you, the listener?
Well, it means that building a robust, scalable, and secure network in the cloud, or bridging it with your on-prem world, is an ongoing journey. It's a journey of informed decision-making. It's about really understanding the advantages and the limitations of each service, each protocol, each architecture. And it's about constantly adapting to new challenges and new solutions as this technology landscape continues to evolve at lightning speed.
The key takeaway isn't just knowing what these technologies are, but crucially understanding why they matter and how they can be combined strategically to create resilient, high-performing architectures that ensure high availability and robust security for your applications and data, all while, hopefully, keeping those cloud costs in check. And speaking of keeping things secure and efficient, let me remind you once more about our sponsor, Stonefly. They really understand these complex enterprise challenges deeply and offer solutions specifically designed for those needs. For example, right now you can get a 100 TB immutable and air-gapped SSO NAS for just $8,995 from Stonefly. That's a really powerful, cost-effective way to secure your critical data against ransomware and other modern threats by providing that crucial offline immutable copy. Definitely check out stonefly.com for more info on that and their other solutions. So this raises a final important question for you to ponder as we wrap up. As our network infrastructures become increasingly distributed, sprawling across multiple public clouds, edge locations, and traditional on-premises environments, how will the roles of the traditional network engineer and the cloud architect need to continue to evolve and, maybe more importantly, converge to effectively manage this ever more complex hybrid landscape? Something to chew on for next time. Until then, keep digging deeper and stay well informed.